All right, so let's get going. Sorry to start a minute or two late here. At 11:31, I realized I didn't have my class notes. I'd left them at home, and so I ran 3 red lights, one across Willamette Street, and passed an old man who was going too slow, and I feel lucky to get here this early. So I didn't get caught going 50 in a 25. Anyway, I didn't admit that on camera either. Okay, let's start. Today, we're going to finish things off. New place. And so I'm going to finish off. We did Logit, and we did a couple models last time: limited dependent variables or truncated variables, censored regressions, limited dependent variables, where your dependent variables discrete, zeros and ones, it's limited in some way. We talked about a couple of those models last time. I've got one more of those today. So I'm going to start off with a summary of what we did last time and what you need to know from it. Then I've got one more model today. Then I'm going to go on to maximum likelihood. And I'm not going, it's pretty technically difficult, maximum likelihood. I'm not going to hold you responsible for it all. But I'm going to make an endogenous on how much you pay attention. And so if it looks like people are paying attention, I probably won't ask you to do much. If it looks like you're just blowing it off and leaving and all that and acting like you don't have to know it, then I'll make the requirement much more difficult. So I'm hoping you'll stay and pay attention, and I can just say, here's what you need to know, just this little bit, but we'll see how that goes. But first of all, I want to straighten up what we did last time as best I can. So last time we did 3 different models, depending upon sort of what our data looks like. So the first model was to deal with data where your dependent variable was a 0 or a 1, and you're trying to measure a probability. So we looked at the probability of buying a car. It could be the probability of voting for a candidate, the probability of buying the good, the probability of any sort of thing. And you have a whole bunch of data on individuals, and all you know is whether they did or they didn't. And from that yes, no, 0, 1 structure, you want to estimate the probability conditional on some x's. We can get the unconditional probabilities pretty easy. Just take the total number of people, the number of people who bought it. Those will be 1s over the total number of people. That's the percentage you bought. That's an estimate of the probability. But we want to condition that on income and other sorts of things that we know about the individual. How does their probability of this purchase vary as their individual characteristics vary? So we can't just stop with a simple average. We want a model that models these probabilities as a function of some x's. So that's what we were up to. So the first model we wrote down was the linear probability model. And it looked like all of our other models. I'm using t's here. I probably should use i's. It's probably better to think of this in a cross-section of people. So let me switch the notation. So the data on y is 0 or 1. So in these kinds of problems, yes or no, did or didn't. Whatever you're measuring the probability, voted yes, voted no, for or against. Voted for the candidate, against the candidate. Bought the good, didn't buy the good. So the data on y is just this. Your x's are the normal sorts of things like income and whatever other characteristics you might think matter. Then we showed there's 2 problems with this model. The UT is not normally distributed. And 2, that UT is heteroscedastic. And the solution to the heteroscedasticity problem is just as usual. Estimate the variance through some model, divide through by the standard deviation, and go to town. So the correction is the same as always. There's nothing new in terms of correction. So what you need to be able to do is describe the model. What's this model look like? And show these 2 problems. And I did this last time, explicitly in class. Showed that UT was not normally distributed because it can only take on 2 values. It's actually a binary random variable. For a given x, Once x is fixed, we showed that ut can only take on 2 possible values, so it can't be normal. And then we also showed that it was heteroscedastic. So that's it for that model. Describe it and describe its problems, describe the solution. But the solution you already know, and the problems are these two. Okay, the second model we looked at was called a Probit model. We start off with these kinds of models with some unobservable y. So yt star, yi star is alpha plus beta xi plus ui. And the way we model the choice in this regression, so in this one we're actually modeling the choice. So we're going to say that yt equals 1. This is what we actually observe. This is unobservable. So yt star is not something we can observe. What we do observe is the choice. So we observe yt equals 1 if alpha plus beta xi plus ui is greater than 0. Basically, if this thing is greater than 0, this doesn't have to be 0, but you can always renorm it to be 0. So this might be saying that if you're offered a wage greater than the reservation wage, you take the job. And all we observe is you take the job or not. We don't observe the actual wage offer, which is what we'd like to observe. So what we observe is if the wage offer is bigger than the reservation wage on this side, they take the job. If we get yt equals 0 if alpha plus beta xi plus ui is less than 0. Their wage offer is less than the reservation wage. So the structure's a little bit different. So describe the model, what it looks like, how it works. The reservation wage model is a good example. This could be whether you purchase a good or not. This could be consumer surplus. This is your value, this is the cost. The difference is surplus. If the surplus is positive, you buy the good. If the surplus is negative, you don't. But the surplus is not observable. But nevertheless, we can make inferences about the choice from merely observing what your choices are. Now, to estimate this, you have to use maximum likelihood. So this has, and this is something you'll understand better later today. So let me just write it down. This has the likelihood function. What I want you to know is this, and to estimate it, you have to use MLE. Then I'll tell you later today what you need to know about MLE. But for your information, so to estimate this, you have to use maximum likelihood estimation, which you don't know yet. So this is the model. To estimate it, you have to use MLE. That's what I want you to say. The actual likelihood function is the product of all the times yi equals 0. So this is the product over all y's that are 0. This is the probability that y is 0. Minus alpha minus beta xi over sigma times the product where yi equals 1 of the 1 minus f, 1 minus the same thing, f of minus alpha minus beta xi over sigma. This term here is 1 minus f of alpha minus beta xi over sigma. This is the probability of observing a particular sequence of data. But we'll come back to this later. And so for these kinds of models, we've got this unobservable thing determining your choice. And all you can observe is the choice. This is how you would model it. And you would estimate it with maximum likelihood estimation. That's it. That's simple for that. Then we had a third model. And that's called the Logit model. Okay, so the Logit model looks like this. It's the log of the probability, 1 minus the probability, is alpha. These are PIs. Well, I'll just leave the i's out. That's how we did it. So these are probabilities. So this is between 0 and 1. What we said last time is this function takes a 0, 1 variable and maps it into a minus infinity plus infinity variable. So it takes something that's got a limited support between 0 and 1, which can't be normal, and it changes it into something that could be normal. So it just changes this p to run from minus infinity to plus infinity instead of 0 to 1. Since a normal distribution runs from minus to plus infinity, that's neat. Yeah, go ahead.
So it changes the discrete variable to a continuous?
No, it takes a continuous variable in a 0, 1 range, and it moves into a minus infinity plus infinity range. So it's often, as I said last time, we often do this with unemployment. Because you know that 0 is less than the unemployment rate is less than 1. So if you have the unemployment rate as your left-hand side variable, this can only be between 0 and 1. So you can't have a shock over here of 37. Well, a normal random variable is going to have a possibility of having a shock of 37. So it couldn't possibly be normal. One way out of that box is to use the log of u over 1 minus u. That's going to go from minus infinity to plus infinity. You don't have to worry about the boundedness of your left-hand side variable. And so it's a way of dealing with that problem. In this model, so you estimate this somehow. So you estimate this equation. Then you find that P equals 1 over 1 plus e to the minus alpha plus beta x plus u. So this is the model that tells you how the probability changes with the x's. It's called Logit because this is a logistic distribution, but I don't really want to get into that. So this is the way you'd estimate this model, and then you could derive the probabilities this way. Now, the reason this is a useful model, what we like about this model compared to the other ones so far, is that we're guaranteed that the estimated probabilities will be between 0 and 1. We're not sure of that in the other model. Go ahead.
In my notes from last time, I'm showing the equation as just 1 plus e to the negative, like not 1 over 1 plus e.
That would, if I wrote something down different last time, it was wrong.
I'm a bad note taker.
I don't know that. I sometimes think of other things and write things I'm thinking instead of what I should be writing, and so I could have. I could have been thinking of the distribution. I'm not sure I want to get into that. I'll leave it at that.
I have that in my notes.
This. Okay. One, if the data is such that the y0 is less than yi is less than 1. It's important I don't have equals on either side. You can estimate with OLS. your left-hand side variable is just yi over 1 minus yi log. That's an estimate of the probability. So you just use the yi's that you get. So, you know, if the yi's are actually probabilities or fractions or something, you can go ahead and just estimate this model right here with OLS. Just take your data, transform the left-hand side, and use OLS to estimate it. So it's really easy if your data is continuous and doesn't ever be 0 or 1. When it's 0 or 1, when pi or yi can be 0 or 1, that means this is either log of 0 or the log of infinity, which is a problem. And you have to use other techniques to estimate it. So the second thing we said last time is if, this is just like the last model in that sense. The second thing is if y equals 1 or y equals 0, as in our first example, say, then you have to use maximum likelihood estimation. And we haven't talked about that yet. So this is what I want you to know. Here's the model. It's nice because we're guaranteed that p is between 0 and 1. It's not hard to estimate in this case. You just use OLS. In the other case, you use MLE. And so really that's what I want you to know. Okay, let's do one last model. I think this was pretty easy to understand, at least the problems. So let's do limited dependent variables. So this is another class of models. These models were mostly about probabilities, trying to estimate the probability of doing something. This is just a problem of limited dependent variables. So what do we mean by that? In some case, the 0, 1 case would be a limited dependent variable. But in the last case, we're really mostly worried about discrete left-hand side variables. When it was 0 or 1 mostly. So it was the discreteness of the left-hand side variable that was causing most of the problems. You can see in this case, when it's not discrete, there's no problem. You just use OLS. So really, the last section was all about the problems that occur when your left-hand side variable is discrete. You try to use OLS, it's not normal, you get biases, so we go to these other models. Then they're harder to estimate because you have to use MLE. This is a different problem. So let's just take a standard yi is alpha plus beta xi plus ui. And here's the problem. We only measure, let's just say y cannot be negative. And this one probably works best with an example. Now I'm going to switch the axes because in economics we get them mixed up and I want to get the causality right. So I'm going to put the interest rate on this axis and investment on this axis. Because I'm thinking that interest rate causes investment. They're negatively related. So when the interest rate is low, this is a low line, investment is high. As the interest rate goes up, investment falls. And at some point, we might think that investment, the interest rate's so high, it's 39%, that anything higher than that, you won't invest. There's no projects that'll earn enough to justify buying money at some rate. So at some point, this hits 0. The question is, what will our data look like in this model? And so if we think about the scatter plot we'd like to have, in this range, as long as the interest rate's between here and here, it's not a problem. We'll get normal looking scatter plots. But once we get out here, what will we observe? Suppose the interest rate's there, what will we see? We won't see this point on the line down here, we'll see that, right? And so I'll start to observe a bunch of 0 values in here as the interest rate gets too high. Because the interest rate's so high, we don't just start tearing stuff down. You don't negatively invest. Because you just don't borrow money to make new investments. And so you'd see the data sitting here on this horizontal axis for all those eyes. Where up here you get normal looking data scattered around the line. If I fit a line to that, what's it going to look like? It's going to be too flat because it's going to try to fit these points rather than this set of points. So when I fit a line, it's going to look something like that. It's going to try to hit these points. And so it's going to have a biased slope and a biased intercept. Because of the truncation in the data. Survey data does this all the time. It'll take certain income classes. Income, I said that I used an example of $1 million in the census for a while. Any income over the $1 million was simply coded as a million. So in the data, once you hit a million, it just leveled off. So if you were trying to explain something, and you're looking at the data, once you got to a million, it just leveled off. And so if you're trying to explain income inequality or something, your data was going to misrepresent the answer. And so that truncation could be a problem. Could be on both ends. Sometimes you only observe income greater than 20,000, less than 100,000, something like that. And everything else is thrown into the endpoints. They do that a lot. Then you're going to have data that has two. It might look something like this. You might have a flat part at the beginning and so when you try to fit a line, you're going to get it wrong again. It's going to be too flat. So this truncation problem is going to throw off your intercept. In one case, this is not the only example. Let me make sure you don't. This is just one example. Any sensory truncation of the y values is problematic. Now, if my data was only in this range, I'm probably okay. So when I actually have data down here, that I've got a problem. One solution might be, well, let me just throw all these out. Just throw them out. That works. But throwing information away is almost always less efficient than using it somehow. There's information here. And if we can use it somehow, we can maybe improve our line. I mean, think about it. If you know this point is here, can your slope ever be out there? It can actually help you to bound the slope. So this has information in it. You know the slope can't be any flatter than the first point you see there, up to a random error. And so it helps you bound where your slope can be. If I throw that information away, I don't have that bound anymore. And so it's tempting to just take this information and just toss it away and say, okay, I'll just throw it away. Estimate with the observations that aren't censored. That'll work, but it's less efficient than taking account of the information that you have. Because there's information there that we can use somehow. But it's not a linear kind of a thing like we've been using before, so it's kind of hard to take into account. But once we do, we're better off. Okay. So, OLS is biased. That's what I'm showing here. I'm not going to show you formally. We could, but there's no sense in doing it. So OLS is biased. Here's what the model generally looks like. So let me just write down a description of the model. So the way to represent this mathematically is to say that if, say, yt is greater than 0, this is just an example. This could be any number. It could be less than something too. It's just a truncation point. And yt is equal 0 otherwise. 0 if yt is less than or equal to. That's basically that. Here's yt. 0 can never be negative. And so this is describing this kind of a model. So your yi, you observe it when it's greater than 0. I'm mixing up my i's and t's, sorry. And all you observe is a 0 when y is negative. You observe 0 instead. If the errors are normal, use MLE. What you do is look for the lim depth procedure and use lim depth. These problems are more micro than macro. That's not really an important distinction. Well, that's all I really wanted to say about those models. So we'll go on here to maximum likelihood. That's all right. Next time, you'll turn in your projects. I'll put them in a pile and say, any questions? So long as there are, we'll stay and answer them. When the questions end, the class ends. Or when 12:20 comes 1:20, whichever comes first. Okay. Well, I'm putting this off because I know you're going to be put off yourselves. But maybe not. So there's a variety of different ways. You know, where did beta hat come from? Where did this beta hat equals the sum of the xi minus x bar, y minus y bar, sum of the xi minus x bars? Where did that estimator come from? You found it from minimizing the sum of squares. So one way to get an estimator is to minimize the sum of squares. That is not the only way to derive an estimator. You can also use something called the method of moments. There's something called maximum likelihood estimation. There's more than one way to derive an estimator. Often you get the same exact answer. The method of moments, least squares, maximum likelihood, all give the same beta hat for the basic regression model. You get the same estimator, but they're very, very different approaches to the problem. You take more advanced statistics, you'll learn even other ways. This is one way to derive estimators that always works, and it has some really, really nice properties. These estimators are always consistent. So if you have a maximum likelihood estimator, it's consistent, period. They're also asymptotically efficient. So they're consistent, they're asymptotically efficient. You can't get an estimator with a smaller lower bound, with a smaller variance. It achieves the Cremier-Rao lower bound, we say. And let's see, consistent, efficient. Dang, I lost it. Well, I've got it written down later. I can just cheat. Oh, yeah. Asymptotically normal. So the estimators are normal. You can use normal distributions on the things. That's all great. Why don't we just do this all the time? Because it's hard. And you have to use maximum likelihood estimations. You have to kind of build up to it from simpler stuff. You have to use nonlinear estimation techniques. You have to use optimization techniques. In the old days, this was really hard on computers. And it was easier to find estimators that were simpler. More and more, we're able to just directly do maximum likelihood estimation. And more, that's just what we do, because it's so much easier. And so, for the most part, these days, these estimators are always available. You can always find them. And once you have them, they have these nice properties. Properties I'm going to want you to know. And I'll write them down soon. They're consistent, efficient, and normal. All the things we hope for from an estimator. Okay, so what the hell is it? I was so embarrassed. My first paper I turned in grad school, I spelled likelihood with a Y. I got corrected. I'm still embarrassed to this day about it. So I'm afraid to write that word. I'm sure I've spelled other things wrong. Somehow that one really bugged me. I was pretty embarrassed. I should have known better. Okay, let's suppose that x is distributed normally. So x is a random variable. It's distributed normally with mean mu and variance 10. Just to make it simple, I'm going to assume we know the variance. So we're going to assume this is known. Draw a sample of 500 observations of, say, 500 obs. What maximum likelihood does is it maximizes the chance that your data came from a particular distribution. So it's going to find the normal that best matches the data. That's what it does. So I'm going to pick a U, I'm going to pick a mean estimate that maximizes the chances that this sample was drawn from this distribution. If I want to maximize the likelihood that this sample was drawn from this distribution, what should U be? Well, let's suppose that we calculate x bar equals 24.5. What's the most likely distribution that this data came from? My guess is a normal with mean 24.5 and a variance of 10. If that's the mean in the data, this is the most likely distribution to have produced it. So you find the distribution most likely to have produced the data you observed. Now I could have left the variance out. What would I do then? Just calculate the variance of the data and choose that as this and say, okay, it's probably this mean and this variance. That's the most likely distribution that this came from. Now notice I have to make an assumption about what the type of errors I have. It's normal, it's F, it's T, it's something. So I have to make a distributional assumption. That's one thing that you have to do with maximum likelihood. But once you have that distributional assumption made, then everything else falls out pretty easily. But you have to make that initial distributional assumption. Now, I haven't shown you how to get this estimator yet. I'm just trying to explain what maximum likelihood does. So it's just going to pick the parameters of the underlying distribution in a way that, again, maximizes the chance that this was drawn from that data. I mean, if you had to put $1 billion on whether it came from that or that, what would you choose? Which one is more likely to have generated the data you're observing? I'd sure pick that one. By that much money on the line. It's much more likely that this data came from this than from this. Because the mean is 24.5. That tells me a lot that it's probably not that. Especially with 500 observations. And so if I want to maximize the likelihood of winning my bet, I would choose this one. Well, all we do with maximum likelihood is make every possible choice available. And we pick the one that maximizes the chance of winning the day. Of winning. And it's no harder than that. The mathematics can be a little harder. Intuitively, that's it. So it's no great mystery, I don't think, what it's doing. Okay, good. Let's be a little more formal. More generally, I'll do an example that hopefully puts some of this in context. Let x be a random variable with a probability density function. Depending on unknown parameters. Theta. This is a vector of parameters. This might have the mean and the variance in it. This might have beta 1, beta 2, beta 3, beta 4, and sigma squared, that kind of thing. This is all the things you need to estimate. So that's just a set of things you need to estimate. So the probability density function is f of x given theta. So what the hell does that mean? Let me give you an example. You've seen this, a normal distribution. So this is just a normal, f of x given the mean and the variance. Those are the parameters we're talking about. The normal distribution is totally characterized by two parameters, the mean and the variance. All the moments of the normal distribution are characterized by just two parameters. That's one thing that makes it special. Not all distributions are like that, but this one is. So all you need to know everything about the normal distribution is its mean and its variance. The first two moments we said. This would be 1 over sigma square root 2 pi. Remember this? E to the minus x minus u, where u is the mean, over 2 sigma squared. Remember that? That's a normal distribution. Just this thing. Here's x. That's that function. That's the equation of this curve. So put an x in here. It gives you the value. So this is f. Remember, all functions are, you give it something, it spits something back at you. You give this an x, it gives you an f. I give it an x, it gives me an f. Functions are just mappings that take one thing into another. This one takes x's into f's. So I know this, I know this, I know that, I know that. I give it that, it spits back there. And it's normal. I give it all the x's in the world, it maps this out. Okay, that's a normal distribution, that's it. All right, so what do we do with it? If we assume that draws our sample, points in our sample, are independent. You can do maximum likelihood for the dependent case, but we're not going to cover that one because this is going to be enough. Comma, for a random sample of x's, x1, x2, up to, oh, I don't know, xn. The probability of one head is 1/2. What's the probability of two heads in a row if they're independent? How'd you get that? You multiply them together. So when things are independent, the joint probability is the product of the individual probabilities. Right? Probability of xy is px times py if x and y are independent. That's something you showed. Okay, good. These are independent. So what's the probability distribution of the sample? So this product, f of x1 given theta, that's the probability of observing the first x. That's the probability of x1. It's normal. So the probability is just that high. That's the probability of x1. There's the probability of x2. given that would come from some distribution, some mean and some variance. So we're drawing with a given mean and variance. All the way up to f of xn given theta. That's the likelihood function. That's the thing we want to maximize. What does it represent? That's the likelihood, the probability of observing x1 through xn. That's the probability of the sample you drew. If they're independent, each one's independent, we just multiply it together. That's the probability of observing that one, the probability of observing, if they're only heads and tails, probably head, tail, whatever your sequence is in your data, that's the probability of it. It just happens to be normal rather than heads or tails. But it's still just a product of the individual probabilities. Great, great, great. So all we do is pick the theta, the mean and the variance for the normal case, that maximizes the probability, that maximizes the chances that it came from that distribution. We're going to find the mean and the variance that are most likely given our data. So L, the likelihood function, is the product from 1 to n of the f of xi given theta, which we just need that over there. So to maximize, choose theta such that the partial of L with respect to theta is 0. Remember how you maximize something? You take the derivative, set it equal to 0. That's what we're going to do here. Derivative. Take a derivative with respect to theta, set it equal to 0. And then we also need, if it's a maximum, what's the second derivative? It's always the opposite, right? It's negative. The second derivative has to be negative. All right, one more thing. You know what a monotonic transformation is? That's a transformation that preserves order. And so if x2 is bigger than x1, and I do a monotonic transformation, x2 is still bigger than x1. It turns out that maximization problems are invariant to a monotonic transformation. So we can take the log of this, maximize the log of this is the same as maximizing the function itself, and that makes it much, much easier because the log is a monotonic transformation. It doesn't ever double back down, it always goes up. And so when you apply that transformation, it's order preserving. So wherever your peak was relative to the rest of the data, because if this is always still bigger than this and still bigger than the one on the other side, it still has to be the peak because you preserved order. So the peak point doesn't change in a monotonic transformation. And so we can do these monotonic transformations at will to make our problem simpler without changing the value of the maximization that we calculate. So we're going to simplify. We'll take the log. And that is a monotonic transformation, which means it doesn't change the max. So what we'll do is take the log of that thing, the log of L of theta and x is not the product, but rather it's the sum. And the derivative of the sum is a lot easier than the derivative of a product. So that's what I want to do. So this is equal to the sum from 1 to n of the log f of xi given theta. So it's the log of f of x1 plus the log f x2 plus the log f of xn. So that's what we're actually going to maximize. So we'll choose theta such that d log L d theta equals 0, d2 log L d theta squared is less than 0 because maximum, maximum. Okay, let me write down the properties, and then I'll do some examples that'll hopefully make this all come together much clearer. Right now it may not be particularly clear, probably isn't, but we'll get there in a second. So 3 properties, already set them, then we'll do an example. And we're making good progress, so we may even end early, I don't know. Started late, might as well end early. It's a non sequitur, right? It's okay. Properties. MLE, maximum likelihood estimation, in case anyone missed that along the way. 1, they're consistent, but biased in small samples. So they're consistent, they're not unbiased. We'll see that in a minute when we drive some of these estimators. I'll show you that very thing soon. But they are consistent, so with an n large enough, we should be okay. They're asymptotically, when I say that I mean large n. They're asymptotically efficient. We just mean if the sample's large enough, if the sample goes to infinity, they're efficient. So, and this is the lower bound thing I was saying. For large n, that is asymptotically again, no other consistent estimator has a smaller variance. So they're fully efficient. The ratio of the variance of this estimator to any other estimator is less than 1. That's not a very good way to say it. It's more efficient than any other estimator. That's a much better way to say it. And for testing, the nice thing is it doesn't matter what distribution you start with. There's a few little regularity conditions and things we're skipping over. But basically, for anything you can start with, the estimates are asymptotically normal. So U hat, beta hat, those kinds of things are all normal when they come out of maximum likelihood. They're asymptotically normal. So for a large n, MLE approximates a normal, even if you start with non-normal errors. Okay? So this is true even if the underlying distribution of the x's is non-normal. My example over here was all about normal random variables, but you can do a likelihood function for any distribution. We're just using normal as an example. So those are the properties. I'm going to want you to know that no matter what. You probably figured that out. So you're going to need to know the properties, at least a vague description of these things. I'm really happy you seem to be paying attention. So far, just a vague description. Here's what it is. You're maximizing the probability that this thing comes from a particular distribution, and then the properties here. But let's do some examples, try to show you how this all works. And I don't have that many, so we're getting there. Maybe this isn't as hard as I'm making it out to be. Let's let x be normal with mean mu and variance sigma squared. So these are the things we don't know. I'll do a regression example in a minute. I'm going to do non-regression examples. So we're not estimating betas yet. We're estimating something else. But suppose we're doing that. Okay. We have a sample from x1 to xn. And for an individual observation, let's assume, well, we already have. The distribution is f of xi given mu and sigma squared. So this is our distribution. It's just 1 over sigma square root 2 pi, normal thing, I'm there, normal thing, e to the minus xi minus mu over 2 sigma squared. For as few as they are. It's going to shut the door, but oh well. So what's the likelihood function? It's a product of these things. So the likelihood function, what we want to maximize, we want to find the estimates of mu and sigma squared. So what I want to get out of this is estimators for mu and sigma squared. So I want to find the maximum likelihood estimator for this and for this. That's our goal. So we write down the likelihood function, L of u hat sigma squared hat. That's what we want to find, given our data, is this product, 1 over sigma hat square root 2 pi e to the minus x minus mu hat x1 over 2 sigma hat squared. I'm just putting the hats into the estimators I want to find. That's times then, that's the probability of x1. Probability of x2 is the same thing. Control C, Control V, replace 1 with 2. That's what I wish I could do. I have to write the whole stupid thing again. So it's the same thing. I'll replace 1 with 2. Because it's the probability of the second observation rather than the first. They come from the identical distribution. So Control C, 1 over sigma hat square root 2 pi e minus x2 minus mu over 2 u hat 2 sigma hat squared times dot 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 1 over sigma hat square root 2 pi e to the minus x n minus mu hat over 2. So multiply all those together, and you'll get the likelihood function. All we have to do now is take two derivatives. Take a derivative with respect to u, set it to 0. Take a derivative with respect to sigma squared, set it to 0, and solve those two equations for u hat and sigma hat, and those are our estimators. We're done, essentially. So once you all you do is just take the probability distribution which is given to you. If they're independent, you just write out the product of those things. That's what you have to maximize. But again, it's going to be easier if we take the log likelihood, so let's do that. Because you probably don't want to use the product rule over and over and over and over and over here. It's no fun. Then you'd end up dividing through by all the product terms. Well, never mind. If you can see it in your head, great. You have to drive this, you've got the U hat in every term, and so this, you'd have the product rule gone wild. And that's going to be hard. All the other terms are going to drop out. Never mind. Let's just take the log likelihood. Let's take the log likelihood to make it simple. So the log L of U hat, so that squared, given the x's, turns out to be minus n log sigma hat minus n over 2 log 2 pi. We usually throw that out because that constant doesn't matter. When I take the derivative with respect to u or sigma, it's not going to be there. So there's no sense carrying it around, but I don't want to confuse you by dropping it, so we'll leave it there. But there's no need for it. Minus 1 over 2 sigma hat squared times the sum from I equals 1 to n of the xi minus u hat squared. So when you take the log, it reduces to this. Way simpler. Use the fact that the log of the sum is the sum of the logs, log of the product, and then, or excuse me, the log of the product is the sum of the logs. And then all these terms you can put into one. There's n of these terms. You get one here, one here, one here, so you get n of those. You get n of these here. And then you're just left with this term. The log of e gets rid of the e, and you're just left with this part. So let's find u hat. So what do I have to do? Take the derivative with respect to u hat and set it equal to 0. So we do that. So for u hat, the first order condition, the only place that u hat is in this term. So it's minus 2 over 2 sigma hat squared times the sum of the xi minus mu hat times minus mu hat, and that equals 0. Divide through by this and this, which I can do. Those are just constants. So the sum of the xi minus, those are xi's, minus mu hat equals 0. Sum of the xi equals the sum of the u hat i's. Sum of the ui's. From 1 to n, that's n u hat, so u hat. I did that kind of fast. So I just took the derivative with respect to u hat, set it equal to 0. Just divided out all the constants, which we can do always. Divide by that. Divide both sides by minus u hat. Divide both sides by that. They go away. Left with this part. Distribute the sum inside. This is a constant. So this is like n times u hat, right? It's u hat plus u hat plus u hat plus u hat n times. So you get n u hat. And this one is just the sum of the xi. So what's your estimator for the mean? Surprise, surprise. It's the sum of the xi's over n. That's the maximum likelihood estimator of the mean. That's a way to get that estimated. Exactly what you've been using. We can find sigma squared or we can find sigma. Doesn't really matter. Let's find sigma squared next. It's a little easier if you've... Oh, no, let's differentiate with respect to sigma, sorry. So let's find the other estimator for sigma. So what's the derivative? So now I just take the derivative of this thing with respect to sigma. Not sigma squared. Sigma is easier because I don't have a sigma squared here. So it'll be easier to do with respect to sigma hat. So the derivative turns out to be minus n over sigma hat minus 4 minus a minus 4 sigma hat over 4 sigma hat to the fourth times the sum of the xi minus mu squared. And that has to equal 0. So we take the derivative, set it equal to 0. And then you do some algebra, and you'll get that the sigma hat squared is 1 over n times the sum of the xi minus mu squared. I skipped the algebra part, but it falls right out. You can just drop this term here. Anyway, no, I didn't say that. It comes out that if you work it all out. Now, what's different here? What's the estimator you learned for the variance? 1 over n minus 1 times this, right? You usually put n minus 1 here instead of n. So when n gets to infinity, the n over n minus 1 becomes trivial, right? A billion over a billion minus 1 is so close to 1 we don't care. But 3 over, what am I saying here? Totally lost my train.
3 minus 1.
Was that? I know. But I don't know where I'm going with it. I know it.
That's not trivial.
It's not trivial.
That's 1.5.
What was I talking about?
As n approaches infinity, it's close to 1.
Oh, yeah, the bias. I just like went out the window and it wasn't coming back. Thank you. The bias here. What I'm saying is you learned, when you had a regression model, this was n minus k. When you had just a regular old thing, this was n minus 1. But the bias, which is n over n minus 1, goes to 0, basically, as n goes to infinity. The difference between n and n minus 1 goes to 0 as n goes to infinity. And so asymptotically, it doesn't matter. That's why it's consistent, but it's biased. So maximum likelihood does this a lot. It'll give you a biased estimator, but it's consistent. This is not the estimator we want in small samples. Because what you would do here is you'd have to put in the x bar you got over there for this estimator. And this has to be n minus 1, because you only have n minus 1 degrees of freedom. And so once you put in your other estimator here that you've derived already for u hat, this is the sum of the xi over n. This has to be n minus 1 to be n biased, but it's not. Now let me do one last example.
Is that sigma to the fourth in the denominator?
Yes. Yes. To go from here to here, here's the steps I left out. The next step is minus n over sigma hat plus 1 over sigma hat cubed times the sum of the xi minus x minus u, x bar is what that's going to be, squared, equals 0. Then you just say, okay, 1 over sigma hat squared times the sum of the xi minus mu squared is equal to n, and then you can get that answer. Just flip those two. You multiply through by sigma on both sides. That gets rid of this and leaves an n. Just moving n to the other side. You've gotten this in sigma squared now. Then it's just a matter of flipping both sides, putting that over there and that over there. So that's what I look at. Okay, one last example, and then we can leave. Oh, you've been so good today. I feel like being really nice. I shouldn't treat you like kids. You're not kids, you're adults. Good is the wrong term to use. Let's suppose yi, let's do a regression example. Yi equals, I'm going to leave out the constant just to make it easy. What's the maximum likelihood estimator of beta? What's the MLE of beta? I claim it's the least squares estimator, you already know. Let's prove that. The likelihood function for this turns out to be the product from I equals 1 to n. I'm assuming the errors are normal. So we're assuming that UI is normal 0 sigma squared. So this is the likelihood function for the UIs. Each UI is normally distributed, they're independent, so the product is the joint probability, the probability of observing that sample. That's the same as the product from I equals 1 to n of 1 over sigma square root 2 pi e to the minus yi minus xi beta over 2 sigma squared. Now we take the log to simplify our problems. So take the log. Turkey, I didn't need to write that. My cousin's name. Take, not turkey. Okay, so the log likelihood, I guarantee we'll finish it. Beta hat, sigma, given x. I just want to estimate beta hat. Turns out to be, once you take the log of that thing, minus n log sigma minus n over 2 log 2 pi minus 1 over 2 sigma squared, sum from I equals 1 to n of the yi minus xi beta squared. So all I have to do is take the derivative with respect to that and set it equal to 0. But notice something. You see any betas there? I don't. Betas there? Anything in there? And get rid of all those. Not going to change the problem. Maximizing log L is the same as minimizing the sum of the squared errors by finding beta hat equals the sum of the yi minus xi beta squared. That's the sum of the errors squared. So what you did was minimize the squared sum of errors. That's exactly equivalent to maximizing the likelihood. This is a negative here. See that negative in front? The thing that makes this biggest is the thing that makes this smallest, because you're subtracting. So the way to make this sum big is to make this thing small as you can make it, because there's a negative in front of it. So maximizing this is the same as minimizing this. When you minimize this in your last class, that's how you got beta hat. So you get exactly the same estimated out of maximum likelihood that you would get from minimizing the sum of squared errors. I need to let you know. Somebody have a question? Then it says one last thing, and it does everything we just did in matrix algebra. I don't think so. I tried that once. It didn't work. We're not doing that. So if I have to end early today, then that's a reward. So be able to describe maximum likelihood intuitively. I don't think that's too much to ask. Know the properties of maximum likelihood. I should make you do this. It's not that hard, but